Okay, so let's go to Senthil's question, design criteria for bare metal versus RTOS. So basically it has many dimensions to this. For example, what kind of application are you talking about, right? Or product are you talking about? So that is where it starts. Basically, how complex or simple it is. Let's talk about a simple embedded application, right? So you're just designing it. It takes a couple of input signals, and then it's a control application. So the application can be a control application, or a computational application, or a communication application, or a combination of all this, right? So let's say there is a next question about fan controller, right? So you're getting temperature input, maybe the fan current speed input, and then your output is basically to the control signal for the fan speed. It's a very simple single purpose application. And of course, you could have a little more elaborate. So the question is number of IO interfaces being handled. That is one criteria. And basically both input and output, and how are they competing? Basically, how are they laying out themselves in real time, right? Then, of course, constraints like memory constraints that you have, both code memory and RAM memory. So we are talking about constraints. This is another criteria you would take into account. And then cost. So basically, there are multiple costs. One is basically, if you look at what an RTOS does, RTOS provides modularity to the code to organize time-dependent processing logic, right? So basically, a task. Task is nothing but a function, and it is invoked based on some events, and it does some control or computational processing, and then it again waits for an event. So basically, that is very easy to conceive. And in a bare metal, you do essentially the same thing, except that if you saw the foundational video on that, you would understand event-driven paradigm. So basically, in a bare metal, what you have is one loop. One is called a major loop, or it's a major loop, right? And then you check for various events and decide to call the event handler of that event. If there are multiple events, you will complete one and then come to the other. So there is a implicit priority ordering here. It's burnt into the logic here. That means in the order in which you are scanning, so this state, you may have whatever the sequence in which you are checking, basically you have an implicit priority. And then therefore the interactions among various event processing dependencies across event handling code is tied into the code, code. So tomorrow, if you want to change something, you cannot just make a change to one place. You have to make sure that all the interleaving patterns are okay and they're not violating any timing constraints, etc. So that is where. So when you talk about interactions and dependencies, the bare metal non-OS environment makes it harder to make changes. Make changes as locally or so. So that is where RTOS helps. RTOS basically separates the priority concept, and the logic, the event handling logic. These two are separated. This is where the scheduler comes into picture. And event handling, you focus on the, this is the focus of the application. So by changing, so while writing the code, you don't worry about this too much about the dependent or otherwise. You just use the mechanisms for synchronization if there are dependencies. For example, data dependencies. So you wait for an event or wait for data, the producer consumer kind of situation, right? So all these are easy when you have an RTOS. It basically separates the concerns. So the concerns of logic, right, versus the time ordering or time interleaving. That is the whole thing about RTOS. Of course, RTOS come with additional features of memory management. Maybe we are talking about fixed size memory management, memory pool management. It may have other higher level abstraction for synchronization. So in the bare metal, the only mechanism you have is to disable or enable interrupt. This is the only mechanism you depend on for critical sections, etc. And then you implement all the synchronization using application variable, flags and variables and so on. And so basically, it's basically putting a lot of load on the application developer to think about these things. So those things are, which is very typical in embedded systems, have been taken care of by the RTOS primitives. So what is typically across applications required, it is already available in an RTOS. That is the advantage of an RTOS, right? However, all this takes code size and RAM, of course. For example, the task control blocks and whatever, all the control information has to be stored in memory. So if you have a very limited memory, like some applications are 2K or 4K RAM, which is on the microcontroller, you won't even be able to fit the RTOS there. Even if you strip the RTOS of all inessential modules, the basic scheduler, task management is a minimum required element of a RTOS. So you won't be able to fit, or you'll be not able to support all the features. So the constraints are, of course, the memory constraints. There could be cost constraints also. Of course, memory costs also are included, but if you have selected a microcontroller with a certain configuration that is bundled in this, if you can select a smaller memory CPU or MCU, it may provide more on-chip peripherals for the same cost, maybe more on-chip peripherals. For example, you may have an ADC or extra channel of ADC DAC or something else, more GPIO, etc. So basically, it's a processor decision, but the role of using an RTOS in this choice of the MCU is also there. The RTOS itself may be free or royalty-based thing, right? So there is a cost to using an RTOS. The other thing, there are other hidden costs to that. If, for example, you're using an RTOS, then if you are porting your application very frequently, you have to make sure that RTOS is available for the next platform, next CPU or MCU. That means that port has to be available. Many times, in the good old days, you had a lot of new ARM processors coming, and RTOSs were available for some and not for the other. Now, of course, it's much more prevalent, but it may change tomorrow. So availability of an RTOS on a particular MCU platform itself may become a constraint. So that is another constraint. But there is also a bug. You have the application. You may want to change from RTOS 1 to RTOS 2 or bare metal, in whichever direction you may port it. So you need an application abstraction layer, OS abstraction layer, to protect the application from these changes. And of course, this means if it is designed with that OSAL, then you're okay. But if it was not originally designed with that, then it basically comes with the cost of having to abstract many OSs, the services of the OS, right? It also adds to the additional layer means more overheads, function calling overheads and so on, in spite of all the tricks of macros and so on. So basically RTOS comes with, so RTOS means overheads. Primary decision criteria, is it worth it? Is it worth in terms of the overheads, in terms of the cost, and is it in terms of even knowledge? So if you have a team which is to learn an RTOS things, it's a learning curve involved. So sometimes in projects you have to take decisions of this, especially in very low end, low cost products. Many times what happens, hardware engineers will be doing the firmware development, and they know how the IO works or the peripherals work, and they can do C coding, let's say, but learning an operating system, RTOS, and especially the principles of synchronization, etc., the mutexes, all these are learning curve for them, not just the RTOS APIs, but knowing these concepts. For a hardware engineer who has done the board development and he is going to write the software for the product, then these are barriers, learning barriers, right? So it can also play a role in a project. So it's not purely technical. The technical advantages of an RTOS is primarily separation of concerns and abstraction, but there is overhead. Those are also technical concerns. Cost is a business concern in terms of choice of components, licensing cost for RTOS, tools, maybe even tools. So when you're debugging with the RTOS and without RTOS, things can be different. So debugging tools, right? And finally, the knowledge available about RTOS. So these are the various things I can think of. If anybody wants to add anything or make a discussion on that, I'm open.
Hey, Raghu, would it be fair to say that if the product is a connected product, it would invariably require a RTOS environment?
Not really. Again, so it's a connected product. See, this is another thing I missed. Basically, let's take something like a BLE chip, right?
Okay.
You may have a solution, which is a single chip solution, or a two chip solution. Basically, you have the MCU which is doing the application logic, and you may have a BLE chip which is doing the connectivity, right? So the connectivity stack runs here, and application. So you may have some interface to control. It could be UART, it could be SPI, whatever it is. And on top of that, you may have, like, this is a modem. It's more like a modem. Then you may use AT commands or any API wrappers that are provided as driver for this BLE, right? So the question is, connected doesn't automatically mean you would need an RTOS here. There is also in the one chip, there's another strange situation. So you have the BLE hardware, and then the BLE firmware from the chip vendor, which makes the PLE protocol run properly. And then the vendor may give you some kind of application SDK. Basically, you can put your application on the same chip and exercise this. For example, you're developing a BLE beacon-based application. It's a very small application. You might directly put it on this. So if you are developing this kind of a chip, you have to decide whether the application SDK needs to be isolated from my firmware. So there is a requirement for isolation. Basically, you're providing something like a virtual CPU to this. So you need something to manage this separation. So the separation here is not just modularity, but in terms of protecting the logic, the time critical operations here, and application can only do certain things. So the control here over application resides with the protocol firmware. So only when it has done its things and there is spare cycles, it will call or it will give control to the application. So you need to have some kind of scheduling mechanism built into this chip. In this case, you don't need, it is hidden from you. You're having two separate processors. So there's physical CPU, two separate CPU. Here you're having a shared CPU. Therefore, if you are developing this product, you may use an RTOS of some kind or a hand-rolled scheduler, whichever you can, to separate the application from this. So the question is, are you talking about, that brings another consideration. What kind of a development model you have, or model? Basically, are you developing entire system, or you're developing only part of the system, application versus the platform software? If you are doing two things, if you are a platform developer and you're going to give it as SDK to different applications, maybe it's a good idea to have an RTOS. If you are an application developer and you don't want to know about the details about the platform software, again, RTOS separates that nicely. But if you have basically a single dedicated team doing the entire thing, so if you are doing this entire system development, maybe you don't need an RTOS. You don't need to you may still structure the software well, separate the application from the platform part, the drivers part. That all modularity principles are applicable, but the control, you have the entire control over the software stack. So you may get away with not having an RTOS there. So connectivity automatically does not mean an RTOS, but it depends on how you are. So basically, what are you saying? We are saying that the connectivity stack, is it offloaded? Is it offloaded, right? Or it is embedded?
Yeah, I think my comment was in the context of running a connectivity stack. Generally, that's complex enough to require an RTOS environment, at least as per my understanding.
Right.
Or
so I'll say, if I am the connectivity stack developer, okay, actually I won't depend on a particular RTOS. I will embed my own whatever scheduler or RTOS within ports, rather than depend on a commercial RTOS, because I want portability of my stack, right? I don't want to know anything about the RTOS, so I take care. So let's say Bluetooth, you have a transmit path and a receive path, and then you have the hardware, maybe a Mac and the baseband hardware, and then you may have some state machines to manage the connection. There's a connection manager, state machine. So I might have very few number of tasks as part of the stack, and I might want to make priorities for a receiver over transmit and so on. I will decide how they are So I may do a RTOS of or scheduler of my own and embed it as part of the stack. So the stack itself can go into an RTOS or a no bare metal system. In all cases, it can run. You don't have to map each of these tasks to an RTOS task and so on. If I put the whole thing in one RTOS task, the commercial aspect, I can manage my time according to this, provided this task is given the right priority between this and the stack priority versus application task. So I would say it's not complex. It depends on what protocol you're talking about, what kind of communication you're talking about, obviously. If you're coming from the Linux kind of kernel world with so many different connectivity options, maybe yes. If you're coming from a pure, single chip solution point of view, no.
Okay.
Okay.
Yeah, I mean, yeah, RTOS portability makes sense. So what we are saying is, but when it comes to porting this connectivity stack to a bare metal, it would require some hand picking or some head editing, right? Or it's just
it
it's just
doesn't.
plug and
Actually,
play.
It's designed for bare metal. It can also be embedded in an RTOS task, right? So basically, what does the bare metal give? The events have to be fed, right? Event pump or message pump. Now, as long as your RTOS can give me that, I'm done. I need not come from directly from the ISR or from the hardware, right? It can come through the OS mechanisms. So all I need is an event message pump.
And I was talking about porting to the bare metal.
Right. So what I'm saying is this is designed for bare metal. Therefore, it can be embedded for any RTOS.
Okay.
Within an RTOS.
So the external interface for the stack is just like, okay, the environment is to feed the events to it and it will run. Okay.
Right. So that's how I make my stack portable to unknown platforms.
Okay. Yeah. Thanks.
So Senthil, you have any more questions? Yeah, go ahead.
No, Raghu, I think it's pretty much clear. Yeah, thanks for your explanation.
So it's not a technical thing, but if you want to prioritize technical thing, look at dependencies, number of IOs, or number of how complex the thing is. How many tasks are you managing? So if it goes above, handful, definitely an RTOS is worth.
Okay.
Then you have other, mechanisms of producer consumer, yes, and you have some RTOSs give you all this priority inheritance protocol. So you don't hold a resource and then priority inversion happens. Those are all sophisticated, advanced things that you use in mission critical systems. Some may give you monitoring features, some may give you deadlock avoidance features. So depends on your needs there technically. Okay, but in principle, you have if you can afford it, use it.
Okay.
But make sure your application is abstracted from the RTOS, so it can run on any other RTOS or without an RTOS.
Thank you.